Hello, I'm going to solve a series of small problems where we'll find a state using the PC model. These are very short snippets of problems, but same methods can be used for more complex problems. So let's begin. The first question asks us to find enthalpy of H2O for a given pressure and saturated liquid. There are two pieces of information given. We have to find enthalpy. Well, the first thing first, we first should draw the TS diagram, trying to figure out where in the diagram the state belongs. So first thing, we do this dome shape. We draw a constant pressure line, let's say it's 200 kPa. That will be the fundamental approach. So this is our 200 pressure equals 200 kPa line. So we know the state 1 will be somewhere along this line, along the constant pressure line. What else is given? It's saturated liquid. That means X must be 0 and pressure must be 200 kPa. That's what is given. X equals 0 means we are somewhere along this line. So this must be an F point, saturated liquid. So this is really simple. So we are given saturated liquid. We have been given pressure. So what is enthalpy then? Simply HF at 200 kPa. So we'll go to the saturation table because pressure is given. So therefore we'll go to the pressure saturation table and we'll seek out. Okay, so we launch the PC model. The pressure is given. We launch the pressure saturation table and we find 200 kPa, which is 0.2 MPa. So if you notice, so this is, we locate our pressure. So therefore we know all these different variables, but we are asked to find HF. And HF can be seen, this is our H. Pressure is shared by this entire row. So 504.7 is our answer. Very simple problem, but let's still go and verify this. So how do we verify? For that we go to a new tab and launch thermofluids.net again, the test software again, and then go to test calc tab and system state and PC model. To launch the test calc, you have to go to this tab, click run, and if that run doesn't show up, you have to click here to make sure Java is allowed. Okay, so what all are given? X, recall that H2 is already chosen here. So X is 0. That corresponds to saturated liquid. And the pressure is, what is given? Let's go check quickly. Pressure is 200 kPa. So we come back, put 200 kPa there and click calculate. And the enthalpy is found right here, 504. As you can see, the answer is verified. 504, and we got 500 here. So we feel confident that we got it right. But just to make sure, we know from our understanding that the F point should be on the left side of the TS diagram. And sometimes a visual confirmation is a great thing. So go and try to do a TS diagram, which is so simple here. And you notice that exactly as we thought, state 1 is saturated liquid, and it's shown here. You can draw a constant pressure line by clicking the constant pressure button here, and you can see that state 1 is saturated. Okay, let's go back to another problem. This time, as you read the problem, let me quickly draw the TS diagram. Always we are going to start by drawing a TS diagram. The dome. Here the pressure is given is 520 kPa, a little bit higher. So I'm drawing that there. So this is pressure equals 520 kPa. and x is 30%, so maybe this is my state 2. We had to find, so these are the information given, find S. So because X is given, we know that we are inside the dome, so we have a saturated mixture. So therefore, we don't have to really figure that out. Some other problems, if X is not given, you have to figure out whether we are inside the dome or not. So to find S, we know S is given by, for a mixture, it will be 1 minus X SF at P plus X times Sg at P. See if it makes sense. X is the quality, that means what fraction of the mixture is vapor or gas. That's the German word for vapor. So X times the G state and 1 minus X times the F state property is what we got at state 2. So basically our work turns out to be 1 minus 0.3 times finding entropy at SF at 520 kPa. Let me not write that, just you understand what I'm saying. SF at 520 and Sg at 520 kPa. So let's go and pick those numbers up. If we go to the saturation table, that's here, and we have a 520 kPa. Again, pressure is known, so we are already in the pressure table. That is from our previous problem. 520 kPa means 500 right here. We get the pen. We have 500 kPa and 550 kPa. Notice these are MPa. The unit switched from that point. So 520 kPa will be somewhere in between these two pressures. And we are supposed to find SF. See, entropy are here, SF and Sg. So SF will be somewhere in between these two. Let's say we pick a value 1.86, 1.89, let's say just 1.87. And Sg is going to be in between those two, 82 and 78. Let's say 81 is our value. I mean 6.81 is our value. So with that in mind, let's go back and plug these numbers in. I believe they were 1.87 we decided, and 6.81. I have already calculated this with a calculator. To save the time, I'll just put the number right now, 3.35, something like this, kilojoule per kg K. Well, let's go verify. Let's find the entropy using test calc and make sure we are inside the dome. So we go back to the test calc. This time we want to find state 2. Notice the calculated state are stacked here. We can go back to state 1, state 2. So we know the pressure, 520 kPa, and quality is known, 0.3 or 30%. If we calculate that, we'll find, notice that state 2 is somewhere here. And if you do a constant pressure line, you can see that there are two different pressures. State 1 has a different pressure from state 2. And our entropy value that we calculated was 3.35, and let's see what we got here, 3.355. Notice that is 3.355, and what we got was quite close, 3.35. So this is way accurate for any engineering calculations. If you're within plus minus 5%, that's more than accurate for any reasonable answers. So what I suggest is that the way I interpolate it, I call that I estimation. Just you look at it and quickly guess. That probably will make less mistake. by interpolating mentally than if you really plug in all these numbers, use a calculator, or do by hand. As you solve more problem and verify using test calc, you'll get better at that. Okay, let us move on to the next problem, finding state 3. This time, pressure and entropy are supplied. And let's assume that, this is a standalone problem. I obviously chose the problem connected with the previous one, but it could be any pressure and any temperature and any entropy. So again, we just draw the pressure line first, 520 kPa, and entropy is supplied. So to know whether we have a mixture or a saturated, superheated vapor or subcooled liquid, mixture is inside the dome. Recall, this is superheated vapor and this is subcooled liquid. So to know whether we are inside or outside, we need to know what is SF at 520 kPa and SG at 520 kPa. We did that in the last problem. So I'm just writing down what is SF and SG. We estimated SF to be 1.87 and 6.81. Don't bother about the unit right now because everything is SI unit. And given S is 3.352, so obviously 3.352 is in between. So we have a state somewhere here. This would be our state 3. So if this is our state 3, how do I find enthalpy? We know enthalpy is given by 1 minus x times HF plus x times Sg. So our first goal is to find x. How do we do that? Again, we use the formula of interpolation essentially. This is weighted average, I'm sorry. SF plus x times Sg, or 3.352, which is our S, equals 1 minus x times 1.87 plus x times, what is Sg? 6.81. One unknown, one equation. If you solve it, you can find x should be about 0.3 because we really borrowed this number from the previous problem. So once we know x, enthalpy can be found very easily. How? Enthalpy equals 1 minus x times HF plus x times Sg, which is 1 minus 0.3 times HF plus 0.3 times Sg. So our job is to now go and find HF and Sg for a pressure of at 520 kPa, right? Oops. So if we go to the table, 520 kPa is again somewhere between these two. We're already in the saturation table, and HF will be somewhere in between these two guys, and Sg will be somewhere in between these two guys. 640 and 665. Let's take it interpolated to be 650. And here, if we 2748 and 2753, maybe 2750. If I take these two as our interpolated values and go back to the PowerPoint, oops, I have to get rid of these guys first, and substitute the newly interpolated value of enthalpy, saturation enthalpy at liquid and saturation enthalpy for vapor. And solving, we get 1280 or something, I believe. So to go and verify, now we put the unit. Do we get 1280? Let's go and check. So for state, this is state 3. So let's go state 3. Again, pressure is given to be 520 kPa, and entropy is given to us 3.352. Notice the test calc can figure out the phase and everything. It's telling a saturated mixture. Here is the phase given to us. And it did find enthalpy to be 1276, and we got 1280, very close. Think of the percent error. It's almost nothing. Okay. Again, if you want to, draw the TS diagram and verify, you will find that it is definitely correct. Visual check can be made. Let's proceed. Let's find another state, state 4. This time, pressure and temperature are supplied. Again, our standard process will be draw the TS diagram even before we start thinking. (520 kPa line), so the state must be somewhere, state 4 will be somewhere along this line. Now the temperature is given to us. How do we know our state is superheated or subcool? Depends on the temperature. So first, let's find out this temperature. What is this temperature? This is nothing but T sat at 520 kPa. Make sense? This is the boiling temperature at a given pressure. The saturation temperature at 520 kPa. Once we know that, then we can compare. Then we'll know what is 425. Is it above this or below this? So to find the boiling temperature at 520 kPa, we go to the saturation pressure table. And again, 520 kPa, we can see it's between 151 and 155. Let's say it's 153. Then we come back here when we say this temperature is 153 degrees Celsius. So if this is 153, this line, given is 425, that must be way higher over there, right? So maybe this is state 4. So obviously state 4 is superheated. Recall that these are all superheated vapor state on this side, subcooled liquid, and this is mixture. So to find the properties, in this case enthalpy, at this condition, again, we go to the superheated table, 520 kPa and 425 degrees Celsius. So to mentally interpolate, again, we'll go there, and this time we don't need the saturation table, we need the superheated table. We have PC model, H2O, and this is our superheated table. So pressure is given between 520 means between 0.5, let me get my pencil, between 0.5 and 0.6, somewhere between these two tables will be our answer. So the temperature is 425, I believe. Let's go and check again. 425. So the pressure is 520 and the temperature is 425. 425 is somewhere between these two temperatures, right? So 425, this temperature is shared by entire row of all the tables. So we are trying to find enthalpy. So the enthalpy should be somewhere interpolated between these two numbers and interpolated between these two numbers for 425, and then interpolated between these two tables for a pressure of 520. This is 50, this is 60. So imagine if you do accurately, you have to do one interpolation here, one here, and then this is called bilinear interpolation. Interpolation among four numbers. We have a better approach. You just look at this number, concentrate, and just go through your logic. 320, 425 is in between. 3272 and this is 3483. Suppose we say it's something like, 3330 or something. You come here. This is in between 3270, 3330. So I think that's a pretty good, if you ask me, something like this is not bad. I mean, these are bracketed by these four numbers, and the accuracy will be just fine. So we'll say enthalpy is And likewise, you can find any other property. Let's go verify, see how accurate or how bad we have been. So state 4, again the pressure is 520 kPa and temperature is 425, right? If you calculate, the enthalpy is found to be the enthalpy is right here, 3324. Not bad at all. We said 3330 and the actual answer is 3324. If you look at the TS diagram, I wanted TS, sorry. Then look at state 4, just like we thought. If we draw if you want to do a constant pressure line through state 4 only, look, we can say select state 4 and we can click on this constant pressure line here, P equal constant. So you get a constant pressure line. And so this is, as you can see, is superheated vapor. And what we guessed is exactly what we got. So chances are we pin down the state quite well. Let's move on. Let's see how many problems we can solve so that we can cover all the different zones. This one is, again, same pressure. Don't worry about same pressure. It could be any pressure. And enthalpy is given. Well, so that makes it a little more difficult because now we don't know. I mean, from the previous problem, we basically know where the state is. But pretend we have not solved the previous problem. So the pressure is 520 kPa. So the state will be somewhere along this line. But enthalpy is supplied, not temperature this time. So what we do, we should find the enthalpy of F at a pressure of 520 kPa and enthalpy of the G point at 520 kPa. If you find the enthalpy here and here, actually, which we just did in the last problem, so let me just write them down. Enthalpy we found was 650 and 2750. Let me just go and actually I picked them up. Let me just make sure they're right. So to find, we go to the saturation table. 520 is, remember, somewhere between here and here. Oops. Enthalpy is here, so 520 is between here and here. Enthalpies are, as you can see, so I actually already came and picked those numbers up. So I said HF is 650 and HG from here 2750. So if we pick these numbers from here, go back and compare that with the H, the H that is given to us, which is 3324. Obviously 3324 is way bigger than H is greater than Hg. So therefore we must be on the superheated vapor side, and the state 5 must be somewhere here. So now that we know the enthalpy and pressure, we can go back. And the question is what? Find specific volume. So we go to the superheated table, look for a pressure of 520 kPa. So we know pressure is 520 kPa and enthalpy is 3324. We have to find specific volume. For that matter, we can find any other property. So let's go find 520 kPa diagram, superheated table, which is this one. 520 is between 0.5 and 0.6, and enthalpy is given to us. So 3320. So if we go find the enthalpy, is somewhere between here and here, and over here enthalpy is between somewhere between these two. So therefore we bracketed for a pressure of 0.52, 520 kPa, which is between these two tables. We bracketed our answer between this and this, and therefore the temperature will be somewhere in between, which is 425, as you can see. Specific volume will be somewhere in between these two guys, right? And if I may just pick an arbitrary value, 0.61 and 0.71, maybe 0.62 and 0.71, let's take 0.63 or something. 0.63 is my answer. So if we go erase this, so V therefore 0.63 meter cube per kg. Let's go and verify to make sure we didn't make a big mistake. We go to test calc, state 5, pressure is given as 520 kPa, and enthalpy was what? 3320 or something? 3324, I'm sorry, 3324. And the specific volume that we get is 0.615. And what did we get? 0.63. So correct answer is 0.615. Again, this difference is much less than 10%. Very good for I estimates. And if you're accurate within 10%, most of your answer will just work out fine. Okay, just one more problem. I know it's getting too long, but this is the last problem, I promise. And then we will have covered different zones, different areas in the TS diagram. So in this case, what is given? As you read, to save time, let me draw the TS diagram. And it's higher pressure, 5000 kPa, and temperature is 25 degrees Celsius. Do I really have to find the saturation temperature here? We know it's 100, sorry, this is 5000 kPa. And this temperature must be way high, right? 5000 kPa. So 25 degrees Celsius line will be way below here, somewhere here. Does it make sense? So at 25 degrees Celsius and 5000 kPa, this has to be my state. Is that clear how we figured out that we have subcooled liquid? Basically, think about it, it's room temperature water at high pressure. If you pressurize water, it will still remain water. So it's subcooled liquid. But if you really want to figure that out, the methodical way to do that is that find T set at 5000 kPa, and that's going to tell you the temperature is way high, at least 200-300 degrees Celsius. Okay, so we now detected where the state is, and the question is find S and H. So we're going to use the SL submodel. If you recall, SL submodel, I'm sorry, not SL, the CL, the compressed liquid. What does that submodel say? It says that V, U, and S are function of T only. So my state 6 that you can see here, to find S is a function of temperature only. So anywhere here from this point onwards to this point, S is same. But we know that this particular point is called F point, saturated liquid, and the value is known. So therefore we are trying to find entropy here. S6 must be equals SF at 25 degrees Celsius. See if it makes sense. In other words, as long as the temperature is 25 degrees Celsius, I can pick any point, and I'm picking the F point because for this we know how to find value of SF. SF at 25 degrees Celsius, we go to the saturation table for temperature, which is T set, and look for 25 degrees Celsius. Yep, it's here. And what is SF? We just pick up the value, 0.3674. We come here and say, we got this number. So we found the entropy of water at this temperature and pressure. Because entropy really doesn't depend on pressure, only on temperature. But then the next question is find enthalpy. And we know for a liquid, the compressed liquid submodel tells us H is given by PV. U is if you know the temperature, this is at sign, pressure VF at temperature. So U and V can be picked up from the table, and pressure is given, so we can evaluate enthalpy. So what is UF and VF at 25 degree? Go to 25 degree table back, and we can pick up this number here. VF is essentially 0.001. There's no point making it so accurate. VF is known, and UF is obtained from here, 104.88. So if we bring this value back to our calculation, what we get is UF is 104.88, and pressure is 5,000, and VF is 0.001. So essentially it's 104.88 plus 5,000 times this is just 5, so 109.88 kilojoule per kg. And of course verification is all the same thing. We go to the test calc and say we want to find state 6. What is given? Pressure is given to be 5,000 kPa, and temperature is given to be 25 degrees Celsius. And you'll notice the phase composition will be displayed as soon as I subcool liquid. And yes, we found entropy verified, and enthalpy 109.89, and we found 109.88. Really accurate. So the answer is verified, and what we have done is we have found a state in all possible zone, subcooled liquid, mixture, and superheated vapor zone. So I'll stop here, and finding these properties can be put to a lot of use when we solve more complex problems. You will see that.